You ever wonder how your favorite music app instantly sorts a playlist? Or how a GPS finds the absolute fastest route through traffic? Well, it all comes down to two really fundamental ideas: data structures and algorithms. So let's dive in and demystify these building blocks that power, well, pretty much all software.
All right, here's our game plan. We're going to start with how data is organized, then we'll look at the recipes that tell the computer what to do with it, we'll see how those two are connected, how programmers manage all this complexity, and then we'll cap it off with a really cool real-world example: data compression.
First up, data structures. Honestly, the best way to think about these is like digital versions of stuff you already know. Filing cabinets, bookshelves, you name it. They're all just different ways to organize information, so you can actually find it and use it when you need to.
And here's the crucial part. A data structure isn't the data itself. It's the system you build around it. It's the set of rules for how you're going to store things, how you'll access them, and how you'll make changes. So, let's start with one of the simplest structures out there: the record. Think of it like a single index card for one employee. It's not a whole list of employees, it's just a way to group all the related bits of info for one single person or thing. And this is a perfect example. This employee record is basically just a container. Inside, you've got these labeled slots, these fields like first name, title, salary. It keeps all of Maria's professional details neatly organized in one spot.
Okay, but what if you want to store a bunch of items and you want to keep them in order? Well, that's where the array comes in. If a record is like one index card, an array is the whole box, where every card is in a numbered slot. We call that number its index.
Now look here. Notice how each slot has its own number, or index, and it starts from 0. This is the array's superpower. If I need to grab the number 18, I don't have to look through the whole list. I can just say, hey, give me what's at index 3, and I get it instantly. That direct access is what makes arrays so fast for certain tasks. Now, let's look at a totally different way to make an ordered list: the linked list. Instead of numbered boxes all sitting next to each other, I want you to imagine a kind of scavenger hunt. Each item, which we call a node, holds some data, but it also holds a clue, a pointer, that tells you exactly where to find the next item in the chain.
You can see it perfectly right here. Each box or node has some data and then an arrow pointing to the next one. The really important difference from an array is that these nodes can be scattered all over the place in the computer's memory. They don't have to be neighbors, and that flexibility gives them a whole different set of strengths and weaknesses.
Okay, so far we've looked at structures that are basically just lines. But what about data that branches out? For that, we have the binary tree. This thing organizes data in a hierarchy, and the best analogy is a family tree, where every person can have up to 2 children.
Here it is in action. You start at the top, at the root, which is 20, and there's a really simple rule. Anything smaller goes to the left, and anything larger goes to the right. This setup is amazing because with every single comparison you make, you get to throw away half of the remaining data. That's what makes searching for something in a tree incredibly fast.
So, we've got these fantastic ways to organize our data, but just having it organized doesn't do anything. We need to act on it. How do we find something or sort it or change it? Well, that's where algorithms come in. They're the step-by-step recipes that our computers follow to get stuff done.
At its core, an algorithm is really just a set of instructions. It's a clear, step-by-step procedure to get from a problem to a solution. Seriously, think of it like a recipe for baking a cake. You follow the steps in the right order, and you end up with a cake. Same idea.
And this quote right here, it nails a really important point. An algorithm is just an idea. The logic behind it can be explained in plain English. You could draw it on a whiteboard, or you could write it in a programming language. The language might change, but the core steps, the logic, that stays the same.
This table lays it out perfectly. On the left, you've got the problem. Here's a list of numbers, what's the biggest one? And on the right, you have the algorithm, the specific set of instructions, in this case in Python code, that actually goes and finds that biggest number.
Okay, so we've got structures to hold our data and algorithms to process it. But the real magic, the secret sauce of programming, happens when you pair the right algorithm with the right data structure. They're a team, a powerful duo, and picking the right combination is absolutely critical.
And that leads us to a huge question. We just saw 2 different ways to store an ordered list: arrays and linked lists. So, which one's better? Should you just always use one over the other?
And the answer is, of course, it totally depends on what you're trying to do. It depends on your algorithm. If your main job is to constantly insert new things into the middle of a list, their performance is night and day. A linked list is lightning fast, while an array can be painfully slow. Let's see why.
See, here's the issue with arrays. Because all the items have to live in these nice, neat numbered slots right next to each other, you can't just drop a new item in the middle. Nope. You have to make room. First, you have to scoot C over, then W, and so on, all the way down the line. If you have a huge array, that's a ton of work. A linked list, it just updates a couple of pointers. No shifting at all.
So programmers are constantly weighing these kinds of trade-offs. And to manage all that complexity, they use a really powerful idea called abstraction. It's basically a way to hide all the messy details so you can focus on the big picture, working with what you want to do instead of getting lost in how it gets done.
This brings us to something called an abstract data type, or ADT. The best way to think of it is as a black box for your data. It gives you a simple set of controls, like an add item button or a remove item button, but it completely hides how it's actually working on the inside. And this is where the magic happens. As a programmer, you can just use a generic list. Your code to add something is simple and clean. Now, under the hood, that list could be secretly running on an array, or it could be running on a linked list. Your code doesn't know, and it doesn't care. The implementation can change completely, but your code stays exactly the same. That's abstraction.
All right, we've talked about structures, algorithms, and abstraction. Let's pull it all together and see how these simple building blocks can solve a really common problem: making our digital files smaller with data compression.
The basic idea behind a lot of compression is surprisingly simple, but it's also brilliant. In any text, some letters show up way more often than others, right? Like E or a space. So what if we give those really common characters very short codes, and give the rare characters, like Z or Q, much longer codes?
This is exactly what the Huffman algorithm does. And guess what data structure it uses? A binary tree, the very thing we were just talking about. It counts up how often every character appears, and then it builds a custom tree by constantly merging the two least common characters together. By doing this, it guarantees that the most common characters end up closer to the top of the tree, which means they get the shortest codes.
And here's what you get at the end: a completed Huffman tree. It's basically a custom-made dictionary for our specific text. See how a frequent letter like E is way up high? To get its new code, you just trace the path from the top. You go right, then right again. So the code for E is just 1-1. Super short. Now let's look at the payoff. If we use a standard code like ASCII, where every single character takes up a full 8 bits, the simple phrase AAGO takes up 48 bits of space.
But with our custom Huffman code, where the super common letter A gets a code of just 0, that same phrase shrinks from 48 bits all the way down to just 11 bits. That is a massive saving, and it's all thanks to a clever algorithm using a simple data structure.
So here's the big takeaway. When you understand these fundamental building blocks, things like arrays, trees, and the algorithms that work with them, you're basically looking at the DNA of all modern software. These simple, powerful ideas are behind everything, which really makes you wonder, with these same building blocks, what's going to be built next?